is Sandrine Heitz. I'm the LCN co-director at Imperial College, and it's a great pleasure to chair today's joint LCN seminar series, which will be on the topic of nanoparticles and labeling. So the format is that we've got 3 talks from our 3 LCN partner institutions. We start off with James Wilton-Ely at Imperial, and then we will move on to Sasha Rakovich from King's College London and Michael Thomas from UCL. So we've got half an hour for each of the talks, and that includes discussions and questions. So we're on a bit of a schedule. So but yeah, it's a great pleasure to introduce James Wilton-Ely, who's a reader in the Department of Chemistry at Imperial College London, and who will tell us about gold nanomaterials for combined magnetic resonance imaging and therapy. Thank you very much.
Great. Well, thank you very much indeed, Sandrine, for the introduction and for inviting me to speak today. Let me just share my slides. Okay, hopefully everyone can see that.
We see it.
Okay, and I'll put it in presenter mode. Right.
Perfect. Thank you.
Is that good to go?
Good to go. Thank you.
Okay, thank you very much indeed. Right, let's just get a pointer there. Okay, so yes, I'm going to be talking about nanomaterials, of course, but in particular as applied to magnetic resonance imaging and therapy. So we do lots of things in the group. Pretty much everything is linked by the presence of a metal in some shape or form. We do a lot of catalysis and various other things. I just put this slide up really just in case there's anybody here on the call who's got an interest in these areas and wants to get in touch to discuss what we do in those particular topics. Perhaps most closely aligned to what we're doing today, or talking about today, is carbon monoxide sensing in the body, which is a very important biomarker actually for many diseases. So a little bit related to the topic of therapy and imaging. So I think it's quite a good idea to start off with a little bit of historical background, perhaps about colloidal gold, or gold nanoparticles, as we like to call them these days. I mean, the Lycurgus cup, or Lycurgus cup, is shown here on the right-hand side. You can go and visit that in the British Museum, and that has colloidal gold in it, which is responsible for these changes in colour under different lighting conditions. And this is actually how nanoparticles have been used for a very, very long time, especially metal nanoparticles, for decoration. But it's also been used for a very, very rudimentary form of therapy. Who knows whether it actually worked at all? This idea of soluble gold and actually drinking gold solutions was something that was quite popular in the Middle Ages, even up into the 17th century. But it was really only with Faraday who put gold nanoparticles on a more scientific footing that when we actually understood a bit more about what they actually were, and they were very small particles, and that they interacted with light in these special ways. And of course, since about 30 years, we've had a lot of interest in nanoparticles, particularly of gold coated with thiols, with sulfur groups, and that's really the focus of what I'll be talking about today. So I think we can start off by mentioning the work of Turkovich in the 1950s. Who was instrumental in providing a relatively straightforward route to nanoparticles. And this was using a citrate reduction method, using a gold-3 salt, which then led to gold nanoparticles with citrate surface groups, which then could be displaced with thiols, for example, to give a functionalized nanoparticle. But really, that's been a little bit superseded by the work of Brust and Schifrin in the 1990s with the direct generation of gold nanoparticles with thiol surface units in a very, very simple, very straightforward way, with pretty good control over the size distribution of the gold nanoparticles as well. And one key thing about this is also that they are then rendered soluble in standard solvents, so you can use solution methods like NMR to be able to probe the surface functionality, though of course there's only about 1% of the mass on the surface as opposed to the gold itself, so there's not an awful lot there, but it is possible to do. Use some solution methods. Also, there have been a few crystal structures as well of relatively large gold nanoclusters. I mean, this one here from Kornberg and co-workers, published in Science in 2007, has mercaptobenzoic acid units on the surface and is around 100 gold atoms. So perhaps a little bit smaller than we would normally consider to be a nanoparticle as such, but nonetheless, nanoscale, and also does give us some information on the interaction of the surface units with the gold on the surface. However, what I'm going to try and tell you today is that we should look beyond thiols, beyond just these ubiquitous sulfur groups that have been used to decorate the surface of gold for many years. Around 95%, I would estimate, of work involves thiols, often commercially bought ones, which leads to quite a lot of the same sort of ideas being explored, by many groups. But I think that the advantage of having a synthetic background, as I do, is that we can look further afield for different sulfur units that we can attach to the surface of these materials. And one particular type of surface unit that we're very interested in is dithiocarbonates, and these are shown here in the top right-hand corner. So this is simply formed by the addition of carbon disulfide to an amine, usually a secondary amine, to make a dithiocarbanate. And importantly, this has two different forms, one shown here on the left, and then another form here called the thioride form, which has multiple bond character between the carbon and the nitrogen. And that will become important later on in my talk. They're very straightforward to prepare, and they've been used for many years, well over 100 years, for inorganic analysis. They form complexes with every transition metal in every oxidation state, and often precipitate out of aqueous solution, which has led to them being used to either sequester metals from polluted water or to analyze the presence of those metals in aqueous solutions. But it's really only in 2005 that Alexander Way and his group looked at the use of dithiocarbonates as surface units for gold nanoparticles, and that really kicked off a lot of interest in the area, in particular from us. So we wanted to find out a little bit more about what these dithiocarbonates were doing on the surface of the nanoparticles. We recognized that, as did others, that they were very, very robust. Once you attached them to the surface of the nanoparticle, they weren't easily displaced. And so this led us to investigate with colleagues in chemistry, Fernando Bresme in the chemistry department, who's a computational chemist, to look at AU20 nanoclusters and use these as a model for nanoparticles. And we can see from the Kornberg crystal structure, as shown over here, that there's a stapling motif that is clearly visible for a gold atom that's been lifted out of the rest of the gold atoms and stapled between two thiolate surface groups. And this can be shown here. And so this is called the stapling motif. And it causes quite a lot of disorder and rearrangement to the surface of the gold nanoparticle. But what we found when we analysed this is that we did indeed get the stapling motif reproduced computationally, but when we used a dithiocarbanate, then we didn't see the same sort of reorganization of the surface structure. So something different is happening with dithiocarbonates, and that perhaps helps also to explain why they are a bit more robust. These units here, this gold dithiolate unit, is also prone to loss as a molecular unit from the surface of the gold structures. This is often not probed by people who do this sort of research, and so it's perhaps just there's a lack of awareness of this degradation route. But dithiocarbonates don't seem to show the same propensity for rearranging the surface and also being lost from the surface. So this is a slide that just perhaps illustrates a little bit better how we use the AU20 tetrahedron to be able to model these interactions. And we can see here that the two thiolates distort this gold atom out of the arrangement that it was previously in, and this is the stapling motif that I've mentioned. But in contrast, we don't see the same effect when we have dithiocarbonates attached to various points on the surfaces, on the edges of the AU20 tetrahedron. Now I should shift gears a little bit and talk about MRI, because this is something that's also going to be very important in my presentation. Now, I think many of you will know that MRI is a very powerful tool that we can use to gather information on what happens in our bodies, in particular in relation to disease. And it's very, very widely used. I think well over 3 million scans are carried out in the UK every year. using MRI machines. It's very, very good at spatial resolution, and it gives good soft tissue contrast in many cases. And the background behind MRI, the principle that underpins it, is the same as that used in NMR. And the images are produced from the protons of water in the body, and processing this signal allows the position and also, crucially, the relaxation rate of these nuclei to be recorded, and the relaxation rate will depend on the environment around that water. Now, the signal intensity is affected by a number of different things. So the number of protons, the spin lattice and spin-spin relaxation time constants, T1 and T2, are also very important. And there's a whole range of contrast agents that are used to try and enhance the contrast through manipulation of those relaxation times. In particular, T1 is what I'll be talking about, because I'm going to be discussing gadolinium contrast agents, which are T1 weighted agents. Now, the problem is that quite often when we do a scan of someone's body, we don't see features that we want to investigate clearly enough, in particular pathologies such as tumours, for example. And so we often need to use a contrast agent, which then boosts the signal contrast, allowing us to visualize these features. And a good example is shown here on the right, where we have a patient's brain here. Before gadolinium injection, it's not possible to see the tumor clearly, but after injection, we now see that the tumor is lit up through the effect of the contrast agent in that area. And the most common contrast agents that are clinically used today are ones such as these shown here, which are monometallic gadolinium complexes. DOTA in particular is the most popular. And these are widely used, routinely used in the clinic all around the world, but only around 20% of scans actually involve the use of a contrast agent. Clearly, it's better not to have to use an additional agent if it's not necessary, but in cases where the features being investigated are very small, it is necessary. And around 700,000 scans every year in the UK involve the injection intravenously of a contrast agent. And one of the reasons why we don't want to use them if we don't have to is that free gadolinium ions are highly toxic. So they have to be bound up in this polydentate chelate that we can see in all of these structures up here. So they're encapsulated, so they can't be lost. And that's really, really important. However, of course, the importance of doing a scan to be able to diagnose disease is very often more important than any small risk that comes from the use of contrast agent. One of the problems with these contrast agents is that they are very widely distributed in the body. They're non-specific in their location in the body, so they just flood the body, and they have a relatively low relaxivity, which is the term that we use to describe effectively the performance of a contrast agent. So we want to try and find ways of improving this relaxivity and hopefully minimizing the dose of these contrast agents being given to patients, given the toxicity that's inherent in using gadolinium. So how can we do this? How can we improve this performance? Well, there are various different ways. I think it helps a little bit to understand some of the processes in play. So firstly, we have to have a water molecule that attaches to the gadolinium center of the chelate, and then this can be through the paranetic dipole interactions of the gadolinium center. It can then help with the relaxation of the protons of the water molecule that's attached, but also this effect is extended out to protons of water molecules that are in the outer sphere, not necessarily attached to the center of the gadolinium, but the distance between them is important. So that's one factor that needs to be taken into account. The amount of time that the water molecule spends at the metal center is also important. But the one aspect that I'm going to concentrate on today is the rotational correlation time. So essentially how fast this whole molecule spins. And these small monometallic gadolinium agents spin very, very fast. And this is a bad thing for the relaxivity, for the performance as a contrast agent. So one way we can try and improve this is by making them heavier, so increasing the mass, and that does work. But also another way is to anchor them to the surface of a much larger structure, such as a nanomaterial. So gold, of course, has been used for many years. We mentioned it just right at the very beginning, and it has a general reputation for biocompatibility. But of course, the use of nanomaterials does have some toxicity risks associated with it, and that mustn't be overlooked. But one of the big advantages of nanomaterials, in particular in cancer, is that the tumours have a very baggy vasculature and wide fenestration, so they actually accumulate gold nanoparticles or nanoparticles of any material in what's called the EPR effect, which allows them to be lodged in there and then not come out, whereas a small molecule such as one of these gadolinium contrast agents can go in and come out without any restriction. These gold nanoparticles in particular have been shown to gather in tumours, which helps. It's a sort of targeting action. We can also make these gold nanoparticles of different sizes, so that will help because that allows us to then control where they go in the body and which membranes they can permeate through. And then, of course, we can change the surface structure. We saw thiols mentioned right at the beginning of the talk. Well, you can have all of these different units on the surface, and this cartoon here on the right-hand side shows some of the possibilities that can be attached to the surface. And this includes targeting as well, which is an important part. You get some passive targeting from this EPR effect, but you can have active targeting through the attachment of antibodies, aptamers, or other small molecules. And this allows us then to have various different units on the surface, combining imaging and therapy or different types of imaging into the same assembly. So the fact that these units attached to the surface, the gadolinium units attached to the surface, are going to tumble more slowly, they're going to move more slowly, have less freedom of rotation internally, means that the rotational correlation time is going to be affected, and the relaxivity of each gadolinium unit present in the assembly is going to be increased. So you're boosting the performance of each of those gadolinium ions. And in addition, you've got hundreds of these gadolinium ions all over the surface. So you have a nice assembly that has very, very high contrast enhancement. And if you can then target that to a tumor, for example, then it should light up like a Christmas tree. So another problem I mentioned earlier was the toxicity of gadolinium. If you don't need to use as much because it is targeted, then you don't need to administer as much. And this is significant because you normally have to give a patient around 3 grams of the contrast agent, which is an awful lot. And given the toxicity of gadolinium, you'd like to try and reduce that if possible. And the possibility of combining this imaging with therapy is something that I'll talk about when I discuss our work in the area. In particular, you can use the nanoparticle itself of the right morphology to be able to excite a thermal response through the addition of usually near IR irradiation of the nanomaterial. And that can lead to localized heating just where the nanomaterial is located, which is targeted towards a tumor, means very, very selective therapy in reducing collateral damage, which is an important factor. Of course, chemotherapy, as we know, has very, very debilitating side effects. How does one go about attaching these gadolinium units to the surface? Well, typically you make a chelate, such as this one here, which is set up for encapsulating a gadolinium ion, and then you have some attachment units, such as thiols, which then will bind to the surface of the gold nanoparticle through the gold-sulfur interaction, which is very strong. So that does work. The problem is you can sometimes get unexpected effects, such as this one here, where the thiols formed disulfide linkages, and you end up having a much more floppy, more flexible surface coverage than anticipated, and this then undermines the enhancement of the relaxivity of the gadolinium ions that you would expect from immobilization on such a large particle. So one has to be a little bit careful. These things don't necessarily always work out as one hopes. So our approach was to combine the use of thiols with the use of dithiocarbonates to functionalize the surface of nanoparticles. And we did this using a modification of the Brust-Shiffrin method, which led to nanoparticles of around 4.2 nanometers in diameter. And this led to around 120 or so gadolinium units on a single nanoparticle. Importantly, we used the dithiocarbonate attachment to attach our most important surface unit, which is the gadolinium unit. And also, because of what I mentioned earlier, the thyroid form of dithiocarbonate means that there is multiple bond character in this carbon-nitrogen bond, which is shown here in red. So there's a restricted rotation around here, and also this amide bond here has restricted rotation as well for similar reasons. And as a result of this, this whole linkage here is much more rigid than it might first appear, and so you don't get rotation around that axis. And this then limits the amount of rotational freedom of the gadolinium unit and enhances the relaxivity dramatically. And in addition to that unit, we can then put on other species which can help with things like biocompatibility, such as the PEG units or the thioglucose, and also the folate unit here, folic acid unit, which can be used to target folate receptors, which are overexpressed in many tumors. We can also put on a unit as one shown here, which is for optical imaging, so that we can then do some cell work and then be able to image where nanoparticles end up in cells before going over to the clinical scanner to look at the MRI performance. When we do that, we use the scanner at St Thomas's Hospital, which is a clinical scanner working at 1.5 Tesla, which is very, very common field strength in hospitals all around the world. And we found that when we analysed these contrast agents on nanoparticles, attached to nanoparticles, we found a 5-fold increase in the relaxivity performance of these gadolinium units when attached to the surface of the nanoparticle compared to Dotarem, which is the monometallic clinical standard, which you can see here. So basically, the lighter the image, the more effective the contrast enhancement. And we can see that it's around around 5 times when you just have the gadolinium units on the surface, and when you have a whole mixture of different units on the surface, as shown here, then we still get a significant enhancement of at least 3 times the relaxivity of the Dotarem. Well, we then thought, following this, it would be nice to try and improve these results even further, and perhaps also to bring in some therapeutic units into the same assembly to be able to have this combination of imaging and therapy. And so we redesigned our surface unit a little bit to make it even closer to Dotarem, because regulatory approval is obviously very important, and to have something which mimics very closely what is already approved is clearly makes sense. So we created this unit and attached it to the surface of the nanoparticle with various other surface units, essentially the same ones I showed you on the previous slide, but with the addition of this zinc porphyrin unit, which I'll talk about in a second. So in terms of the actual performance as a contrast agent, this outperformed our previous design. It's led to up to 7 times higher relaxivity per gadolinium ion when examining the gadoliniums in the clinical scanner. We can see here these results are clearly much brighter than that for Dotarem, indicating a superior contrast enhancement. And when you think about also that you have 80, 90, 100 of these units on the surface of the gold nanoparticle, then in one region of the body you would then have very high relaxivity, so 5,000 or 6,000 in terms of R1 values in the same unit in the same place. Now, adding the zinc porphyrin here gives us access to a therapeutic action, because these porphyrins are well known to be photosensitizers. They interact with light to form singular oxygen and other radicals, which then kill off the cells in the surrounding region. And so we examined this using HeLa cells and irradiated them for 15 minutes at 570 nanometers, and this led to a substantial drop in viability of the cells by 65% when these units were present on the surface. Now, just switching gears a little bit for the final part of the talk, to move from gold nanoparticles to nanorods, and I'll explain a little bit why this was decided upon. It's very much the therapeutic action that was the driver for this. Now, gold nanorods are not so straightforward to make as gold nanoparticles. They involve the use of a seed solution and a growth solution, which then combine together to make these nanorods. And of course, you need to be able to define the aspect ratio as well of the nanorods you make, in particular for the photothermal applications I'll be talking about shortly. And also the procedure to make it involves inevitably CTAB, which is cetrimonium bromide. It's this surfactant down here, which attaches itself to the surface initially, and then you have to try and find ways of displacing that thoroughly or encapsulating it. So there are different options, and we covered that in a recent review, but displacing it if possible. So we only have thiols on the surface, then we can functionalize with our gadolinium units, making use of the effect that I described previously, that these dithiocarbonates would displace the thiols, but not the other way around. So we can post-functionalize with these dithiocarbonates to a nanomaterial that already has a thiol coverage. And here we have some TM images showing these nanorods. GDA, GDB, and GDC are different surface units. They're all gadolinium chelates that are attached to the surface. GDA and GDB are the ones that you've seen already in the nanoparticles, and GDC is actually a tetragadolinium unit. It's one we've designed with 4 gadoliniums in the same molecular structure on the surface. And we can see that they have decent uniformity of size and aspect ratio, and also behave pretty well. We can see that they are similar materials from the UV spectrum here, or the spectra here, and their zeta potential measurements show an acceptable level of resistance to aggregation. However, really important is to be able to remove the CTAB, and that's something that we can see here in this slide. On the right-hand side, we see that the CTAB coated gold nanorods show substantial cytotoxicity pretty soon after you start increasing the concentration of the material that's incubated in the cells. So that is a really important part. But we found that the nanoparticles, the nanorods that were functionalized with our various different gadolinium units, showed a very good stability and a very good lack of cytotoxicity, meaning that they could be at some point progressed into animal studies, which is what we're investigating at the moment. But before we did that, of course, we needed to see whether they really gave us an enhancement of the relaxivity performance, and we found they were actually spectacular in doing that. They gave a 42 times higher increase in relaxivity at 20 megahertz. We're in the process at the moment of getting data on a clinical scanner, which is a little bit further over here, and about 62 megahertz corresponds to the 1.5 Tesla machine. And so what we're getting here is we're getting a substantial, really substantial enhancement of every single gadolinium ion that's attached to the surface of this nanomaterial. But in addition to that, we can use these nanorods for photothermal therapy, and this is something that we've done with the use of a dental laser, actually, that was kindly provided by Dan Elson in Surgery and Cancer at Imperial College, and irradiating the gold nanorods with different powers. We can see that we have different heating effects, so we can get a change in temperature of up to 60, even more than 60 degrees if we heat it at a high power of 2 watts per centimeter squared, and then this drops off with lower powers. We probably want to use something in the middle, perhaps 1.6 is standard. That still gives you around 50 degrees of change after 5 minutes. And then we looked also at the concentration of the gold nanorods. We don't obviously have to add too much, so somewhere in the middle here would be fine. We still get decent increases in temperature, even with lower concentrations of the nanorods. And to be able to stress or kill a cell, an increase in temperature of 10 or 20 degrees is probably sufficient, and so these are far in excess of that. We also saw that the reproducibility of this was very good, so that we could do these heating cycles again and again, and we didn't see a drop-off in the performance. And likewise, we also looked at the TEM images after irradiation and found that the size and shape of these nanorods was essentially unchanged. And then lastly, we looked at incubating these gold nanorods with various surface units in HeLa cells and then irradiating them with light. And we found that we could get with higher power densities of 1.6 watts per centimeter squared, that we would then get, well, about 90, looks like about 90 something percent reduction in viability of those cells, so effectively killing off those cells. We did see a slight difference between whether the cells were washed afterwards. So in other words, there's a certain amount of this effect that's coming from the gold nanorods that are actually on the surface rather than actually being taken up inside the cells, which is something that we're investigating at the moment. So that leads me to the end of my talk, and just to summarize a few points that I've made as I've gone along. So we have a very straightforward method of creating gold nanomaterials, whether nanoparticles or nanorods, using this orthogonal attachment approach of using thiols and dithiocarbonates to put different units onto the surface. And these end up being very, very stable, non-cytotoxic materials that can be used certainly in cell work, and we're translating this now to work in animals. We have a large payload of gadolinium in one place attached to the surface of the nanoparticle, and also because we've engineered the rotation around the tether between the gadolinium unit and the surface using the dithiocarbanate, we can enhance the reactivity performance substantially per gadolinium unit. And then we have observed, in contrast to Dotarem, the clinically approved standard, we get very, very high performance, and this can lead to lower doses of these materials being employed, reducing the risk to the patient. And indeed, some of the ones with the gold nanorods are among the highest that we've seen in the literature. And then lastly, we've coupled this to the therapeutic action, either through PDT with these porphyrin units on the surface, or the nanomaterial itself with irradiation of the material, the gold nanorods, to give us a photothermal effect. And so hopefully in the future, what we'll have materials that can be targeted, visualized non-invasively in the body, and then light pass through an endoscope, for example, to be able to irradiate them and affect therapy in the treatment of disease. So lastly, I'd just like to thank the people who did the work. Of course, it wasn't me. So these people here, Nick, Hannah, Ilchol, and Margot, and most recently, Xin, who's just finishing her PhD at the moment, made a fantastic contribution to this area, and I'm deeply grateful to them for all of their work. Also, I'd like to mention the collaborators in Imperial, Tony Cast and Dan Elson, and also Alkistis, Renee, and Graham at King's College at St Thomas's. Helped in a huge amount with this research as well, and these people for funding. But last of all, I'd like to thank you very much for your attention. Thank you.
Thanks very much, James, for an amazing talk. This was fascinating. We've already got a question in the chat there, or Tan, do you want to unmute?
Yes, thank you very much for a very interesting talk. And I just got a quick question: that how likely you see that GoWin get through the regulatory approval? Do we have some already existing like Go nanorod approved?
That's a good question, very good question indeed. We don't have, I think, gold nanorods approved at the moment, but there is something called Aurolase, AUROLASE, which is, I think, commercialized by a company called, I think, Nanosite. I can't remember, but this is a core shell nanoparticle with, I think, a silica core and gold on the outside, which is used for the treatment of prostate cancer, and I think is being extended to other cancers as well, using photothermal therapy. So they are being used in the clinic. The problem with regulatory approval with nanomaterials is very often because you have a slight variation in size. Regulatory bodies, I think, are a bit less used to this idea when they're dealing with small molecule anti-cancer treatments, for example, which are very standardized. They get a little bit sort of nervous about people saying, well, the distribution of size is this and this, and the number of surface units can vary between this and that. So I think there's perhaps starting to be a change in a realization amongst the regulatory approval people that that nanomaterials can be safe even if they aren't absolutely uniform.
Yeah. Okay. Thank you very much. Thank you.
Thanks. We've got one more question from the chat, and then I think we have to move on in the.
Sure.
But please feel, I guess we can carry on in the chat as well. How upscalable is the functionalization in terms of time versus yield? And this is from Camilla Dondi.
I mean, we tend to use pretty small amounts. I think it depends. I think if you want to talk about the nanoparticles or the nanorods, the nanorods is much more involved. It requires the seed solution and then a growth solution. For the nanoparticles, I think it's a lot easier to make larger amounts. We haven't really made larger amounts, so we don't quite know what challenges would lie if that were to be, to be necessary. I think though that I think the challenges are not insuperable. I think that it would be basically we'd have a smarter way of making these things, and probably maybe even make them in a flow method, so that it'd be made rather than a batch process in flow, and that could help with some of these issues.
Yeah, so that would not be then the limiting step for getting this to. Okay, great. I've got loads of questions as well, but we can thanks. Maybe move on to the next talk. But thank you so much, James. We can carry on the chat. I don't know if Sasha is around.
Apologies, I think I might have gone over. I didn't lost track of time a little bit.
Well, we started 5 minutes late, so that's okay. Yeah. So yeah, thanks very much, and we can maybe keep some further questions towards the end if people want to stick around. That would be good. Okay. So we see you, Sasha. Let
me just share. Hopefully it's still
okay. So I'll just introduce Sasha Rakovich, who's currently a research fellow and lecturer in the physics department at King's College London. After having spent some time at Imperial, and I should say, so that's sort of a very nice LCN story. And I should say that James has spent some time at UCL as well before. So we've got a lot of sort of joint LCN affiliations here, or past affiliations, which is great. So thanks very much for your for presenting today, and we look forward to hearing about your talk on getting a handle on colloidal nanoparticles.
Right. Thank you very much for the introduction. Pleasure to be here today, obviously. And I will be talking a little bit about how we can control colloidal nanoparticles, which I think follows up nicely from the previous talk as well. So yeah, I'm in the physics department in King's College London, where I do some research on nanobiophtonics, or what I call nanobiophtonics. So we work at an interface between nano and biotopics, as pertaining to photonics. So that includes, for example, developing nanophotonic particles for bio applications, or nanophotonic systems for biosensing applications and things like that. So I have one of my PhD students, Miao Zhao, for example, has developed some conjugated polymer nanoparticles that you can use for near-infrared imaging, but also combined for the dynamic therapy applications. So that's sort of in line with what James was talking about in his previous talk, just different material system. And then another direction they have is nanophotonics for clean energy sustainability. One example of this is the work that Steve Poe is doing in my group, and that's development of these biomimetic assemblies of gold and quantum dot nanoparticles for control of energy harvesting, and then redirection of that energy and utilization of this harvested energy for production of high energy chemicals. We also have one more direction, which sort of underpins a lot of the other work that we do in the group, and that is the control and assembly of nanomaterials into hierarchical structures, or the control in solutions. So I have two PhD students currently working on this, and who are Marciano and Anson, who just started, but she's already making some interesting progress on extending these techniques that we're developing to sort of low scale, low cost and large area approaches. Okay, so today I want to talk about this last section of nanomaterials assembly and control. And after a brief introduction, I will talk about two separate ways in which we can control nanomaterials. One is a sort of a passive control where we control where the nanomaterials go and localize them on substrates, and at which point they're no longer able to move anywhere. And the second part of the talk will focus on techniques where we can actively control nanoparticles in solution. Okay. Sorry, I'm getting feedback. I don't know if somebody can mute themselves. Okay. Yep, that's better. So yeah, I don't think I have to introduce what nanoparticles are. Most people on this call would be very much aware of that. Equally, I don't need to sell the promises that they make and the potential applications that they have. But in general, I just wanted to comment that there's many different types of nanoparticles of different compositions, and they include inorganic and organic type of particles with many different possible applications. And in general, there's two ways to prepare these materials, and one is sort of physical, or what do we call top-down fabrication methods, such as, for example, Ebeam lithography. And the second one is usually a wet chemical synthesis method, which produces colloidal particles. And both of them have their own advantages and disadvantages. So, for example, reproducibilities are different, the size dispersions are very different between the two. Also, how we use them is very different. But one of the biggest challenges is actually whether we can deposit particles in a specific location. So, for example, for the EBL-made particles, it's very easy to fabricate them in predetermined locations so that if you do have pre-existing structures, it is easy to create hierarchical and order on the sample. With the chemical synthesis, this is particularly difficult because localization requires some sort of feature of a substrate where the particles are able to recognize and attach themselves to. And so some of the work I did was exactly on that, is trying to guide the particles towards specific locations on substrates. And so the first part of the talk will talk about these examples. And actually, the two-step EBL method I developed while I was still at Imperial, but it's a very interesting method that is very flexible in the way we can use it in research. It basically involves two steps of an Ebeam lithography writing. The first step is where you create your structures. So, for example, you could create just a disk antenna by depositing some gold or other metal through your EBL-defined mask. And then in the second step, you would essentially expose your mask and create two holes in it in a way that is completely and fully aligned to the first layer. So the location of these holes then will determine where your nanoparticles would go. Within these hole in the masks, you expose the substrate and possibly some of the underlying structure as well, some metallic structure. And you can perform some chemistry to attach, let's say, quantum dots to the surface of your substrate or to the surface of the metal structure using very simple chemical methods, so surface chemistry methods. Typically, that would involve functionalization of your substrate via formation of self-assembled monolayer that ends in some sort of reactive groups, and then a subsequent reaction with your colloidal nanoparticle that has complementary functional groups. And so by reacting the two, you end up with a linkage all the way from your substrate to the nanoparticle. So what are the typical monolayers that you'd use for this? Well, it depends on the substrate. For example, many of the metals and semiconductors, they easily accept alkane thiols and derivatives as as a support of self-assembled monolayers. And so, for example, you can easily form an amina thiol monolayer on a gold surface, and then use an EDC reaction with a carboxyl functionalized quantum dots to create a covalent bond all the way from the substrate to your particle. And alternatively, you can functionalize things with, for example, biotin streptavidine functionalization for the monolayer, and then use the opposite for the particle, and that will also create this linkage. If you have silicon or oxygen terminated surfaces, then you can use ethoxysilanes or other derivatives. So APTAS, or aminophosphate triethoxysilane, I think is what it stands for, is an example of that, and I think it's the monolayer that I used in majority of the examples I give today. Okay, so how can we use this method? Well, it depends on what you're trying to do. So, for example, one of the pieces of work that we did with Rupert Alton in Imperial, and the work was done by Michael Nielsen, actually, on the silicon on insulator gap plasma waveguides, where they fabricate these waveguides where you have a silicon waveguide wedged between the two insulating layers, and then on top of that you have a metallic film with a gap in it. And depending on the dimension of this gap, you can move the mode from the silicon to the gap between the two metallic sheets, essentially on top. So your mode will either propagate in the silicon layer, or you will get pulled up into this gap, depending on what the width of that gap is. And the way you can usually characterize these sort of structures is using a cutback method, which involves fabrication of many of these waveguides of different lengths, and then measuring the transmission of light through this waveguide, so the actual propagation of the mode, and outcoupling on the other side of the waveguide. And by characterizing many of these antennas, you can build up statistics and finally have an exponential fit for the transmitted power through different structures. So this is the typical way to do that, but it is quite time-consuming and requires a lot of work, a lot of fabrication, and on top of that, it doesn't actually tell us where the mode is, and it only tells us what is the power that's transmitted. So if you use selectively deposited semiconductor quantum dots, we can actually have both of those pieces of information without having to fabricate many structures. So in this case, we exposed basically a relatively large area on the sample and deposited our semiconductor quantum dots there. So we deposited it onto the silicon and not onto the metal. At least try to, by using APTAS, so that attaches to the silicon surface. And then we used 3-photon excitation imaging to monitor the fluorescence of the quantum dots, so the emission from the quantum dots along the gap of this waveguide. And you can see that from the slice, just from the slice along the waveguide, you immediately get the full decay of the intensity, and from the fit to the model, you can get the propagation length. So you only require one structure to do the whole measurement, and you do not, if you have multiple of these structures, you only need to expose one to characterize all of them if they're repeats of each other. So in a way, it saves a lot of time and a lot of effort. One other thing that it does, it actually proves that in these structures, the mode is confined in the gap, because if the quantum dots are on top on the surface of the silicon, so if the mode was confined within the silicon, you would not get an efficient excitation of the quantum dots, which actually you do see for a wider width here. So this is one example how you can use these sort of methods, and it's to characterize other structures. Another another approach is to, or another application is to actually control the emission of fluorescent particles via coupling with plasmonic structures. So, for example, in this case, I studied the coupling of simulated quantum dots to plasmonic ring cavities, which are essentially just rings of gold. And they use the same method where I expose the gap in the middle of my predefined gold structure, and then attached quantum dots using the EDC reaction within the gold ring. You can clearly see, for example, in the AFM image here, that you get a ring of quantum dots inside of the gold ring, and you can see it in the cross sections as well. So you have quite a good localization accuracy here, and you do see the fluorescence from quantum that's very typical Gaussian shaped peak. So that tells me that any of the chemistry that I did, the surface chemistry essentially, didn't really affect the fluorescence of the quantum dots. What it does do is it allows us to control the degree of coupling between the plasmonic structure and the quantum dots on a large scale. So because we're depositing many quantum dots here, we do not get variations from one quantum dot to the other. We're measuring a collective effect in this case, and you can see that as you make this ring of quantum dots bigger and bigger, essentially the distance between the quantum dot and the gold ring becomes smaller and smaller, and so the coupling gradually improves. And it's very deterministic. You can calculate this theoretically, and the experimental data really does follow the predicted values very, very well. So this is a very nice method for characterization structures, but also for producing sources with specific emission profile and a specific lifetime. So if you can predict both using this. However, it is extremely time and labor intensive. You have to be extremely good at Ebeam lithography and especially at the alignment procedures. It is also quite expensive because the use of BL is usually quite expensive. And because of that, we were in search of other alternative methods. And we got an idea when this paper came out in 2017 from the group of Brugger, who used a capillary-assisted particle assembly method to essentially drive particles into predefined gaps on the substrate using capillary and convective forces. So the idea here is that you have a solution with many, many particles in it, and as you drag a plate that's holding that solution on your substrate across the sample, and at the same time simultaneously heating the substrate, the evaporation of the meniscus will drive the particles into the gaps in the substrate, and thereby depositing these particles. This method is not as precise as EBL, obviously, but it is very inexpensive once you have it set up. It's also not labor intensive once it's set up and running, but it's the actual setting up and running can be challenging because it is substrate dependent. So for every different substrate, you will need to re-optimize the procedure. For every different particle, you also need to do that. It is also not really compatible with pre-existing structures because the alignment is a bit challenging, basically. In the first few instances of kappa method being published, the substrate was also non-removable, so that limited further applications of this. So our contribution to this field was actually extending this technique to work on any substrates in a relatively straightforward way. So this was done in collaboration with a number of institutions, including ICL. And it involved a stamping of the pattern into which the particles were dependent into a PMMA, and then stripping of this PMMA template using a tape. We then used the kappa method that I showed in the previous slide to actually assemble the small particles into the holes. And at that point, you flip the substrate and you flip this PMMA layer with the particles already assembled in it, and you press your substrate, target substrate, on top of it, and then leave everything in acetone to essentially dissolve the PMMA that was holding the particles together. And the PMMA will dissolve completely, will lift off, also lifting off the tape in the process. And that reduces the interaction between PMMA and the particles, and the van der Waals forces between the particles and the substrate become dominant, and so you end up with a beautiful nanoparticle array. And note that there's no dependence on the substrate here. You can use any substrate that you really want, as long as it's not dissolvable in acetone. Okay, so in terms of what you can get with it, well, you can get extremely large arrays of nanoparticles. So here is shown a slide where we've deposited 100 nanometer gold nanoparticles on, this is just an ITO covered slide, with the 400 or 800 nanometer pitch. And both the printing yield and the assembly yield can be quite high, the printing yield especially. So this is the yield of going from the assembly process to the final product. The assembly yield can vary a bit, and you can optimize that through a lot of effort if it's really necessary. Okay, so in terms of accuracy, we measured it to be about 60 nanometers for these particles, so you can measure where each particle should be and where it actually ended up on, and you would end up with something like 60 nanometer variation. And it's slightly better in the direction of viscous flow compared to the direction transverse to it. As I say, it could be used on different substrates. So in the paper that I reference here, we've demonstrated that it works on the gold substrates, ITO films, and gallium phosphide, but also ITO covered with the PDMS layer. And these two structures are particularly interesting because they were deposited on top. Because the gold and the titanium dioxide form a Schottky barrier, and so you can measure a photoelectric current when you shine light on these samples. And when comparing that to just the ITO on titanium dioxide, the additional current that you get has to be from the hot electron generation. So by playing around with the Schottky barrier and biasing things, you can actually measure the energy of the hot electrons with these samples. Okay, so this is basically the two main techniques that can be used for the passive control of nanomaterials. So that's deposition of particles in specific locations, but I have great interest in actually trying to control nanomaterials in solutions as well. Where's the interest coming from? What can we do with it? Well, at the very least, we can apply it for particle sorting, or a temporary or even permanent concentration of samples in solution, and delivery of test materials to sensing areas, or for performing different investigations in solution, so without affecting, bringing in the substrate into the equation, essentially, when we do measurements on photonic systems, on, let's say, a few quantum emitter systems. For the first three, especially, so the particle sorting and concentrations, there's great applications of that in the biosensing area, and that's, I think, primarily where my interest in that comes from. There's, of course, different methods that are available already. So, for example, optical and plasmonic trapping work really well if you only want to trap a few particles and your region of interest is a few nanometers. So for sense applications, for example, you may want to keep a particle in the same place while you're measuring, integrating a measurement. However, realistically, we usually have fairly dilute samples, and we would want to concentrate them. And so other things like other approaches like using dielectrophoresis or even diffusion control can allow you to concentrate the sample if you're able to drive all of your particles towards the sensing area. So the work that we're doing in the area is actually to try and address all of these on a single chip and try to build different components. So currently we're working on separate components, but quite soon we're going to start to work on the integrated system. But here I just wanted to show the two things that we have been developing. So one of them is a combined DEP plasmonic trap, where the structure that we've designed basically involves a bow tie antenna that can be electrically connected, and when you connect this to an AC signal, you will generate dielectrophoretic forces, and these have a slightly longer range than the plasmonic forces. So they typically extend over a few hundred nanometers, whereas the optical forces have a really, really short range. The plasmonic trapping forces will act only maybe 10 nanometers sort of region and the very, very short acting range. So you can easily fabricate the structure. Well, easily, you can fabricate the structure with some sort of success rate. And the DEP forces do act to bring a lot of particles towards this electrode. And I can see whether I can start the video. Yeah. Okay, so when we turn the AC on, you can see that the particles start assembling. So these are just fluorescent beads. And in the video, all I'm doing is swapping the frequency of the AC signal from 100 kilohertz to 4 megahertz. So essentially, I'm following this curve where I'm generating positive forces for low frequencies until I hit a cutoff. So these positive forces drive the spheres towards the electrodes. And then once I pass my cutoff frequency, which is approximately 2.4 megahertz, I start repelling the particles. So if you wanted, for example, to do many measurements on your sample and you wanted to concentrate it slightly, this is a great way to do it, where you can bring your analytes towards your electrodes first, towards your antenna, and then finally use the plasmonic trap and to both perform the final trapping, so to concentrate the sample even more, but also to perform the sensing itself. So the second thing that we are looking at is the long-range transport of nanoparticles using ratcheting Brownian motion. So I'll quickly explain what ratcheting Brownian motion is for those who are unfamiliar. It's basically a rectification of the Brownian motion through the application of an asymmetric potential. So let's say we have a particle which is in one of such asymmetric potentials, and we at some point turn the potential off. So when the potential is off, sorry, having difficulties here. Okay, I'll just talk through it. So if you have a nanoparticle that is trapped in your potential and you turn the light off, the excitation of that potential off, the particle can then diffuse, and of course it will diffuse by some sort of diffusion length that's determined by the solvent and its properties. And let's say it's moved in the forward direction. So when we turn the light on, it will move to the potential well, to the bottom of that potential. When the light is off, it's free to move again, and it can move forward or backwards again. So in this case, I'm showing that it moved back. And then we turn the potential back on, and the particle will again move in the potential. So the trick is to have an asymmetric potential so that the particle has a settling, a trapping sort of position that's not in the middle of each unit cell. But the second requirement is actually more important, is that your time is such that the particle can diffuse to the next unit cell, but cannot diffuse to the previous unit cell while the potential remains off. So obviously if the time off is too small, then the particle will just diffuse within the same unit cell and come back to the same unit cell every time. If the time is too long, then the particle can travel to either of the unit cells, and there's no preferential direction for the diffusion. But if you get your time just exactly right, then while the potential remains off, the particle can diffuse enough to go to the next unit cell, but not enough to go to the previous one. So at that point, you have two choices. It either remains in the same unit cell or it goes to the one that's closest to it. And so in this way, you can rectify the motion of the nanoparticles. Okay, why do we like plasmonics for this? Well, because it's very easy to design things that are resonant at specific wavelengths, and it's also quite easy to apply a periodic potential by just chopping the excitation. So in terms of design, how do we design this? Well, we take our ratcheting wavelength. So in this case, we chose 980 nanometers because it doesn't interfere with any other measurements that we could do in the visible. And then design a dime antenna that has a resonance at that particular wavelength. And then we gradually decrease the size of these antennas so that they become less and less resonant with our excitation wavelength, which is 980. So for example, these three graphs show that each of them has their own resonant wavelength. Each of these three lines are resonant at different wavelengths, but at 980, only the first one and maybe a little bit the second one have any sort of resonance. And actually, the angle is quite important. So the angle theta there is quite important because obviously, if you have no angle, then all three will be resonant at all time, and you have no symmetry in your asymmetry in your potential. Equally, if your angle is too large, that only the first row will actually be resonant, and the other one will provide no enhancement in the electric fields whatsoever. Which means that, again, the potential will be symmetric and there will be no preferential direction for the diffusion. Whereas for 9 degrees, which is the one that we used in the end, you can clearly see that both the electric fields and the potentials extend throughout the structure, and they do have this required asymmetry as shown here. And you can also see that where the bottom of this potential does not coincide with the center of the unit cell. Okay, and so because we have a potential difference, this symmetric potential, we can now drive particle diffusion in a specific direction. So we fabricated these ratchets, and we've tested them on different particles on a very simple setup that essentially involves a laser that's chopped, and then a white light source for dark field imaging, and then a filter to cut off the 980 nanometer laser, and just a CMOS for imaging. And what we do is we track the particles using a MATLAB code that we wrote, and then basically monitor the X and Y deviation of the particles as a function of time. And you can see for when we don't have this 980 laser, the particles remain, the average velocity of the particles, average displacement of the particles is essentially zero with time. Whereas for when we do introduce the chopping, you get a clear difference between the X and the Y direction. So we have a preferential motion of the particles. And this responds to both frequency and power of the 980 excitation. And that's because in one case, we're affecting this time to go forwards and backwards, so the diffusion time of the particles. And in the second case, we need to provide enough trapping power to actually overcome the thermal motion of the particles. So there is an optimum power there as well. I think that's basically it for I just had a couple of videos to show. I don't know if people would like to see them. I think one of them was not bad. So I'm just showing here some polystyrene spheres, 40 nanometers, that they basically just undergoing Brownian motion, so there's no ratcheting. And then once you start chopping the excitation, you clearly see them moving in one direction. It works on different materials. So we've tested, as I say, on these polystyrene spheres. I want to go to the next slide, but it doesn't matter. We've tested them on gold nanoparticles, but with these guys, they're much more responsive, they move quicker, but they're too heavy and they end up sedimenting on the sample. So we'll definitely need to do some surface chemistry there. They also tried it on some conjugated polymer nanoparticles. We can see those little guys move off. we actually see that they gain enough inertia to keep moving in the preferential direction after they exit the ratchet. So that leaves other opportunities to exploit, I think, in the future. But if anybody else has any interest in nanoparticles, please do get in touch with us, and we can try and ratchet them as well, just for fun of it. All right, so my conclusions are basically that there are ways in which we can control nanoparticles now, both on substrates and in solutions. And the work I talked about today is by no means extensive. There's many different methods, and they all have different advantages and disadvantages depending on what you want. But yeah, I'm happy to talk about this with anybody if you're interested. So thank you very much for your attention. And of course, I have to thank all the people that contributed to the work I presented today and the people who sponsored it. So thank you.
Okay, thank you very much, Sasha. This was amazing. So much going on in lots of different applications. We've got time for one question. Sorry, we're running slightly behind. Well, Michael, yeah, get started.
Thanks, Sasha. That was really interesting. I really enjoyed that Brownian ratcheting. I've seen sort of this approach, not the same thing, but conceptually for sort of moving droplets around on surfaces, and I love this idea of you're sort of taking a pre-concentrating, manipulating, driving things into certain areas. I was curious about the kinds of particles you can actually manipulate here. What are the kind of restrictions? I think you've shown many sort of beads. Larger particles. What do you think are the restrictions on the kind of particles you can manipulate? So
in the basis behind this is essentially non-uniform electric fields, and you polarize your material, and then that gets applies a force essentially on it. So of course that is proportional to the volume of the particle. So if you have very small particles, they're not going to be great at ratcheting. On the other hand, if you have extremely large particles compared to the unit cell of your ratchet, then essentially they won't sense the asymmetry in the potential because they're too big throughout the volume. So for every size, you need to design a ratchet in a way. And our ratchets were designed to work between sort of 50 to 200 nanometer particles. But within that, the more polarizable they are, the better the ratcheting will be. But there is not really a restriction on the particles. They work in aqueous solution in this case, but it really doesn't matter. You just need to think about functionalization of surfaces and things like that if you switch the solvent.
Yeah, brilliant, fantastic, thank you.
Okay, thanks very much. We see that you love questions at the bottom right. So I think let's just keep them maybe for the end if there are some, and then maybe we can follow in the chat because yeah, we need to have time to listen to Michael as well. So thanks very much. There was really a lot going on there. So super interesting. Thank you so much. But because we have to move on, let's get another round of applause for Sasha. Thanks a lot, and get Michael on. Michael is a lecturer in bio-nanotechnology and biochemical engineering at UCL, following on from some time at Imperial College. So there is another link here across the LCN. So thank you very much for joining us today, and we look forward to hearing your talk about tailoring the bio-nano interface of gold nanoparticle labels for rapid testing. We can see your slide, but it's not in presenter mode yet.
There we go.
Now it is. Perfect. Thank you so much.
Laser. Brilliant. Thank you, Sandrine, for the introduction. And thank you for the welcome to come and present as well. So yes, I'm going to talk all about the bio-nano interface. I'm going to talk a little bit as well, more generally, about particles that either we are, as sort of the Thomas Lab, as a research group, are developing, but also from my past, as you've referred to, back at Imperial, and some of the collaborative projects that are now coming to fruition as well, between UCL and Imperial there also. So I'm a lecturer in bio-nanotechnology and biochemical engineering. I've got a joint appointment between the London Centre for Nanotechnology at UCL and then the Department of Biochemical Engineering. So all of my students are split between labs in Biochem Eng and then also within the LCN at UCL. Firstly, the Thomas Lab. So thank you to all my students and group members, current and past as well. It's been an interesting start to a lab. So all of my students here, at least, all started in September of 2020. So right in the thick of a pandemic, which is an interesting time to start a PhD at the very least. So kudos to them for doing a fantastic job of that. I'm going to touch on some of the projects very briefly of John and Chapman at the end of the talk, but I'll focus mostly on things that are published, given that this will be a public-facing presentation. But I'll start by just introducing, like, what are we kind of about? What are we trying to do? So we're interested in bridging this gap between advanced liquid handling technologies, biosensing systems that you might find in hospitals, in centralized facilities, and paper-based low-cost diagnostic devices. And we're all very familiar, I'm sad to say now, with lateral flow assays, but it does mean that I don't need to introduce lateral flow assays in too much detail, which is handy. A lot of our group's focus is around the nanoparticle itself, so how we functionalize, how we modify particles, how we implement them in lateral flow assays, and tailor the design and the configuration of the assays to improve sensitivity, specificity. But we also do a lot of work looking at some of the complementary techniques around nanoparticles, things like surface-enhanced Raman spectroscopy and Raman more generally, and how that leads into bioprocess monitoring and some of the analytics required for the manufacture of biotherapeutics and complex protein materials. And then also, in addition, through collaborations within Biochem Eng, particularly with Dr. Stephanie Frank, cell-free expression biosensors as well. And so Dr. Frank at least co-supervises two students here. So John, whose work we'll touch on briefly, and then also Mega, working in these spaces. But I'll focus today very much on rapid tests and nanoparticles therein. Okay, so a great start is always to sort of bamboozle everyone with a lot of information all in one go. So hopefully this is at least relatively clear for everyone. People will be familiar with the concept of a lateral flow assay, this idea of test lines and control lines. What really is going on here is we've got a nanoparticle that's functionalized with proteins that have an affinity for part of an infectious analyte. So perhaps it's a part of a virus, a protein. In the case of SARS-CoV-2, it will be part of the capsid. In the presence of that analyte, particles will stick to a test line that's decorated with another affinity reagent that binds somewhere else on that analyte. And then we might have a control line that just measures for the presence of functional antibodies on the particles to confirm that the test has been stored appropriately. But actually what's going on in these tests is incredibly complicated. So this is not to understand at this stage, but just to appreciate the number of different interactions that are going on here in what's arguably the simplest configuration of a lateral flow assay. So we've got analytes interacting with particles, particles interacting through analytes with surfaces, whether that's via an analyte that's already bound to a particle or via an analyte that's on a surface. And then there's next levels of complexity that you get depending on how you actually configure the way this analyte anchors a particle to the surface, whether it's through additional proteins like streptavidin with a biotin interaction. Anyone looking for a good review on this, I would direct you to Gasparino's paper down here, which is wonderful. But what we've started to do, perhaps in part due to projects kicking off very much remotely during a pandemic, is starting to incorporate some of the underlying simulations of mass transport and lateral flow into the workflows of our projects as well. So I'll come back onto this again in a little bit more detail. But what do we find interesting here? Well, firstly, there's a need for more sensitive point of care tests. I think that's pretty clear from our experience of the pandemic and rapid testing performance at the moment, context and the kind of things you're trying to measure. But actually, there's a huge space to explore for how we can make lateral flow assays more sensitive when you think about how complex the series of interactions are that determine the final binding of particles which we identify at a test line, and looking at the signal to noise that we get from particles at test line versus particles that are non-specifically interacting. So actually, we think there's huge scope here to do a lot of advancement. So I will start by saying that although I've said lateral flow assays need enhancement and improvement in sensitivity, they're actually really good. Given how quickly lateral flow assays work, they're non-equilibrium, very often at least. We're looking at detection of particles through an analyte at a test line over a space of seconds here in terms of the time it has for this analyte to sandwich a particle onto the test line. And so you can actually get sensitivities on a par with ELISAs quite readily with lateral flow because of the fact that we have a porous membrane that's being used as the solid phase to capture these particles. So actually they're remarkably good, but there is a lot of scope to do better. So there's many ways of doing this, and I'm going to kind of go through a couple of different ways that at least we or we've been involved in collaborative projects that have tried to address this in different approaches. And the simplest one to perhaps think about is just make a brighter label. So often, if we're measuring if we're looking at SARS-CoV-2 diagnostic, invariably will be a gold particle, perhaps a dyed polymeric bead. It will just have a strong absorbance. So one particle absorbs a lot of light. And so when we have that single particle bound by one analyte on a test line, it's absorbing a lot of light. It's generating a lot of signal to the signal that you might otherwise measure from just the paper itself that the particle's stuck to. And there's various ways you can do this. You can play around with fluorescence, you can play around with catalysis, which I'll touch on next, and this sort of opacity, like what's the extinction coefficient of the particle itself. And this is a very classic way. People have explored this in many, many different ways. So I'll just pick one example at least that we've explored, and that's catalysis. And so this was a project that was performed by myself, and I would flag Colleen Loynahan here specifically, who was a PhD student I was supervising back in Molly Stevens' group at Imperial. And this focused on the use of catalysis in lateral flow assays. So the idea here is that it's operating in a standard way for a lateral flow assay, binding an analyte that's sandwiching a particle onto a test line. In this case, we use streptavidin biotin to anchor this construct. And this actually comes back to this whole concept of all these different mass transport equations and what they're doing. And what we were really interested in is if we use catalytic particles, how does that affect the limit of detection and the performance of the assay? So what we had was platinum particles, porous platinum particles, that were able to transform a colorless chemical substrate into a colored substrate or colored product. In this case, it was a precipitating product, so it would decorate locally around wherever the particles were, an insoluble black product. And we wanted to see how much sensitivity improvement we could get from this. So the particles themselves were something akin to this, or actually in reality larger than this. This is easier to resolve the porosity. But it's small, few nanometer clusters of platinum coalesced, forming into these larger, highly porous platinum nanoparticles. And we could modify the surface here by passively absorbing proteins, antibodies onto the surface that would decorate between various stabilizing polymer reagents like polyvinyl prolovane. These were seeded growths, so seeded around a gold core, to help us control polydispersity of the resulting systems. And these could generate this amplification. And what we saw was a very nice amplification. So if you look at the data on the left, this is pre-development, so pre-addition of the chromogenic substrate and peroxide, hydrogen peroxide. And this is just due to the inherent absorption of the particles, which also look black. So at high concentrations of an analyte, in this case an HIV P24 capsid protein, we can see the color of the particles, and at low levels, we can see the development of this precipitating dye product. And this allowed us to significantly improve the sensitivity of these lateral flow assays. We were getting about 100-fold enhancement in sensitivity, limit of detection, versus just the color of the particle, and detection of HIV P24 just beneath the picogram per mil regime, which for lateral flow is actually, that's really very, very sensitive for a 20-minute assay. we then evaluated this as well in terms of performance with clinically relevant seroconversion panels. But besides just making something that's brighter, for the same size at least, you can also think about the size of the particle. And again, thinking about mass transport, that's heavily dependent on diffusion, and diffusivity is very dependent on size. So, we can have benefits of having a larger particle, but also there can be downsides as well. So it's quite a complex equation, but you can just increase the particle size generally to improve performance. And so I really wanted to use this as an opportunity to just flag something hot off the press. And so this is a study that's been quite some time in production, I guess, led by Ben Miller, who I think is on the call as well. And Ben's a postdoc that's been working with Professor Rachel McKendry, who of course everyone will be familiar with from lateral flow research as well as general biosensing research within UCL's LCN as well. And this paper was essentially looking at how, by considering the spectral overlap between particle extinction spectra and the sensitivity of different RGB sensors on imaging equipment, you could actually do some very nifty background subtraction work to suppress the noise coming from, or the background signal coming from, your nitrocellulose membrane. This is the paper membrane of lateral flow devices. And this works really, really nicely. But I wanted to just cherry pick one example from here, which is the use of these larger particles. So these are roughly 500 nanometer beads. We elected to decorate the surface of these beads with smaller roughly 20 nanometer gold particles and distribute them spatially to a point where we didn't have too much plasmonic coupling, which ensured then that we had to a degree at least, a discrete plasmon response that then we could use this background suppression approach to minimize background signal generation. And given the size of these particles, the influence of the background suppression technique and the sensitivity of the lateral flow assay format, which was employed, which was comparable to the platinum nanoparticle paper we just covered before, you then get this fantastic sensitivity just based off absorbance of the particle, not including any catalysis at all. So it just goes to show that tailoring the particle and the way that we set up the particle, but thinking carefully about the assay design, can give you really nice enhancement in analytical sensitivity of the device. And so one thing also just to push whilst we're here is Ben's created a fantastic limit of detection software, which is available on GitHub and also in MATLAB as well. So if you want to do any limit of detection analyses, any comparisons, t-tests to look at significance in differences of limit of detections, and this is built off the foundations developed by Holstein and a paper from Jaeger's group several years ago, you can use this software now to easily do this and automate this process. So please do take a look. So another strategy, as you might have guessed, is to think about this nanobio interface. So, I've so far used these lovely pictures that suggest that we've got lovely oriented affinity reagents, in this case IgGs, decorating on the surface. In reality, this isn't necessarily the case. But I'll come on to that in a second. But what is it that interests us when we're thinking about this nanobio interface? And it's essentially it's the number of affinity reagents on the surface, but more important than that, it's the number of functional affinity reagents on the surface. So we can sort of allude to this in a sort of very simplistic way by thinking about receptors on cells. And so Purcell, Berg, and Erickson, Goldstein, Holwalker, Baird, there's very basic models you can use that can treat how an analyte, when it's diffusing towards a nanoparticle or a cell in this case, specifically speaking, can react at the surface and generate an effective sort of particle association rate. And it's essentially dependent on the density of the binding sites. So you're kind of considering it as a fully reactive sphere where you're varying the fractional coverage of the surface that's able to bind. And what that kind of tells us, unsurprisingly, is that the more binding sites we have on the surface, the faster the associative rate. So if we can jam more antibody reagents, more binding reagents on the surface, we can increase the rate at which analytes bind to the surface. Or if it's an analyte on a solid phase, the particle can bind to that analyte. And that's quite interesting. It's very simplistic what we're talking about here, but you can obviously see that by increasing the number of antibodies on the surface, this effective particle associated rate goes up. But actually, it's the associated rate of the individual antibody that we're loading on the surface that makes a very drastic difference here as well. But this model's simplistic. It's not considering steric hindrance and several other local concentration effects, but it gives us a sort of a feel for the importance of antibody coverage. And this is something that's well known within the field of biosensing, of course. So what do these antibodies actually look like on the surface? Well, one of the most common methods for putting antibodies on gold particles is passive physisorption, kind of chemisorption, depending on how you define it. It relies on the fact that initially electrostatic forces are driving approach of proteins onto the surface, and then there's some level of reconfiguration and adoption of different configurations of the protein, perhaps denaturation to a certain degree, representation of concealed functional groups on the amino acid sequence that leads to robust binding on the surface. And this is actually the standard approach used by lateral flow assay developers for conjugating to gold. It's just really easy and it actually works very well. Over the timeframes of assays, of course, we heard from James earlier on where we were talking about the importance of the linkage that you have to the metal surface. And if you're injecting something into a person, that's very important for the long-term performance of that. In this case, we're only interfacing with complex biological samples for very short periods of time. So actually, passive adsorption works perfectly well for that kind of conjugation. But, sorry, let me talk about characterization. So there are various different techniques that we use to characterize this passive absorption when we're developing these particles. One is, conveniently, gold has a lovely surface plasmon, localized surface plasmon resonance, so we can monitor based on the changing local dielectric, the binding of proteins on the surface by shifts in peak plasmon resonance. We can also use techniques like tunable resistive pulse sensing to look at population, individual components of population variation in particle size and charge, as well as DLS. And we can see transitions here as we bind on the surface, as we affect the overall hydrodynamic radius diameters of the particles. We can get an idea of coverage densities and orientations of antibodies on the surface. But of course, this all needs to be consolidated with the actual performance and binding of analytes. So often this is then coupled with assays to quantify the number of analytes that are binding to particles, the number of antibodies loaded on particles, and then starting to understand in its entirety what the resulting physisorption profile looks like. But yes, in reality, physisorption's quite a mess. So you don't really get preferred orientation on the surface. You get a lot of denaturation. Certain studies even talking about sort of having 4% functional antibody on surfaces of particles. So actually, there's a lot of scope to do optimization here. And the effect of this is in determining the availability of these functional binding sites on our antibodies, whether it's denaturation of protein that's affecting the availability of a binding site or just steric hindrance and presentation. We find actually that physisorption is pretty poor, despite the fact I said earlier that it works very well, which actually it does because it's an effective way of loading so many antibodies on the surface, but actually we can do a lot better than this. So one approach that was published quite recently, and this was a project that was again from a collaboration between the Stevens group at Imperial and the Tudor-Sama group, and Dan Richards was a postdoc that was initially with VJ in chemistry at UCL and then moved over to Molly's group, and Dan and I worked together on this project to show a different way of approaching this passive absorption. So the idea here was to use an anchor protein. The anchor protein would passively adsorb onto gold, but it had click functional handles on it, and these could be then used to orthogonally modify orthogonally modified IgGs that were functionalized themselves through a bromopyridazine dione chemistry that VJ's groups developed. And the idea here was to say, well, okay, let's not denature our antibodies. Let's attach them by flexible linkers and show what kind of benefit you get from that. And you do see quite a striking benefit. So for the same loading of antibody on the surface as when you passively absorb the antibody directly, this red trace here, you see a very significant increase in sensitivity of the particles that have been produced to binding of the analyte. And so this also makes us think about, it's not just potentially presentation and orientation of the antibody, it's also flexibility and reconfigurability of the antibody on the particle surface. And this again comes back to what James was referring to of what's the conformational freedom of the structure that's bound on the surface. And in that case, for relaxivity, it was having it more restricted is better, but for antigen binding, having it more flexible is better. So interesting, we've got a different challenge there. But what we found here was a much more complex way of doing it and a much more involved way of doing the modification, but this improvement in performance. So kind of where do we go next? And this sort of comes on to the things that we're kind of actively trying to do at the moment. So in particular, how do we use the smallest binders we can find, present them, and maintain this conformational and conformational robustness of the protein, but also presentation and availability of the binders. And so there's quite a nice literature precedent here of the fact that this electrostatic initial mechanism of interaction of proteins on gold can lead to orientational control. So if you have anisotropic distributions of charge residues, functionalities on proteins, you can take advantage of that and use it to help you orient on charged surfaces. But what's kind of missing here is an underlying kind of rule book of how to generate a new affinity reagent and orient that on the surface of a particle. And so this is what we're looking to do at the moment and are well into the process of doing. And the candidate system that we're using is nanobodies. And this is versatile because the expression of nanobodies is relatively simple. The modification is simple. And because of their low molecular weight, they lend themselves well to some simulation studies as well. And so just a little snapshot of some of the things that we're doing at the moment. So John Ireton has been using a very nice software called Pigbee. This was developed by the Barber Lab and is available as a sort of a tool for biosensing developers to use. We've been looking at developing different nanobody sequences with different functional tails and probing how these adopt preferred orientations on charged gold surfaces. So we can see here by varying whether it's charge, whether it's chemical functionality of the different tails on these nanobodies, we can tailor the preferential binding of these structures in silico. And so now it's a case of validating that through experiment and comparing and contrasting through all the different techniques we've just talked about. So this is current work and will be the next steps, hopefully reported at some point in the near future. And I just wanted to touch on the last thing. So there we're talking about improving the particle K-on, availabilities of binders on the surface and this rate of association of analytes to particles. But actually, it's not always as simple as that. So the kind of the models that we've looked at in terms of the mass transport equations that we're working with are much more complex than this. And so some of the modeling that we've done, this was done by a final year undergraduate student, Devika, during the pandemic. And what we did was we implemented various mass transport equations to model very simplistically signal generation. So this particle analyte receptor construct concentration at a test line as a function of a few parameters. And you can really just see here how things like particle concentrations can make a significant difference in analytical sensitivity for certain associative rates, for example, but you also reach regimes where with high enough associative rates, decision making on where we're focusing attention in developing nanomaterials and surface modifications for use in lateral flow. And here's just a nice example of that earlier schematic, which shows in an example system where we have a relatively low associative rate, actually the majority of the analyte is bound to receptors and not labeled by particles. Whereas in reality, we can only measure this RPA construct. And so it really goes to show some of the challenges when you start to break down what's actually happening in these lateral flow assays. One of the challenges here is we say, well, okay, let's just work with a much higher particle concentration. But the previous example we gave here doesn't take into account non-specific interaction. And actually, we always have non-specific interaction between particles and surfaces and test lines. So really trying to mitigate against that is very challenging. And so just one last thing. One of the projects that we're really interested in at the moment is how we can get around some of these kinetic limitations. And so whilst I can't talk about it here, what we're doing is developing cleavable chemistries, and this is work being done by Chapman. And this is then exploring how we integrate those cleavable functionalities, orthogonal cleavable functionalities, into the diagnostic cascades to enable us to circumvent some of the kinetic limitations. And we're really interested in how we can use this to reduce non-specific signal generation, but also improve analytical sensitivity at the same time. So that brings me to the end of what I wanted to cover. Again, just very much acknowledging the group who are fantastic, and it's a real pleasure supervising such a great team, a very sociable team as well. And a thanks to everyone that's affiliated and related to the work as well, and particularly our co-supervisors and supporting labs as well. Thank you to the funding bodies too, and thank you very much for listening.
Thank you so much, Michael. This was amazing, and yeah, so careful, and you know, every time I had a question, then you sort of answered it already in your talk. So that was really great. We have a bit of time, or we have negative time for questions. So if anyone would like to ask anything, please feel free.
Sandrine,
yeah,
I have
Ian, go for it.
I put my hand up. I wasn't sure if you were checking. Not urgent, but beautiful work. And a very dumb question from a non-expert. But if you're considering using genetic modification type methods, then why can't you just load up the FC fragment of the antibody with cysteines so that you can just bind it directly onto the gold?
So thanks, Ian. That's a really good question. So people have explored playing around with the FC to this end, and conveniently, at least, the FC does present a different charge distribution to the remainder of the IgG, which is where some of these first studies in protein orientation by electrostatic induced orientation kind of came from. And you certainly could look at doing that. I think there would be practical challenges in producing IgGs that bear that many cysteine-free sulfur hydryls on the surface. I think expression there could be very challenging. The other thing is just that the size and the dimensions of that are challenging. So we were kind of really curious about how we could increase this loading occupancy of binders on the surface of the particles. So the nanobodies are so small that it lends itself to upping that density further and creating a much more sort of thin surface modification on the surface, whereas the IgG is actually quite big. You also tend to generate non-specific interaction quite frequently from the FC of the IgG, which isn't necessarily desirable. It's very helpful for generating a control line in current lateral flow assays. And if you were ensuring you had perfect orientation, perhaps it wouldn't manifest as much non-specific interaction. But there's a few reasons there why we'd consider not using IgG in the development work. But mainly for the nanobodies, it's about the simplicity of that expression and the simplicity then of the resulting protein structures that we're actually trying to vary.
Yeah, thank you. Yeah, it's size basically that's a limitation.
Yeah.
Okay. I don't see any further hands up. I just had a question on having gone through a few COVID tests recently. You have to. I mean, you're talking about the speed of the signal coming up, but there is also the fact that it is invalid after 30 minutes or something like that. So why is that? It does seem a bit suspicious to me that you wouldn't want to leave it for as long as possible And you know, why would a line after 1 hour not be a reliable signal?
So sometimes it's very dependent on what the test is, but one of the reasons you can have invalids later is if you have colloid that's not bound at your test line specifically, drying, it can non-specifically adhere to the test line as it's drying and propagating up the strip. And so that 30-minute point is where that starts to become a bit of a risk. And so there could be several reasons why they might suggest a limiting time frame, but that's also one of them, is that you can sometimes start to generate a non-specific false positive because of that.
Okay, so it's not a sensitivity question or anything like that. Okay, good to know. Well, or it might be, but in some cases not. Okay, great. And okay, I don't see any other questions. So yeah, also these talks are recorded, so if anyone has had to go or nip out and come back, they will be available on YouTube. So feel free to get back to them. I think that's a question from Tan. So it will be available for record. Okay. So if we've got no more questions, unfortunately we'll have to wrap up. But it's been wonderful to hear from you all. So thanks very much to James, Sasha, and Michael today. So a really great array of nanoparticles and labeling. So that's great to see. Thanks a lot, and see you next time, and for the next joint seminars or earlier. Thanks a lot.